This watch has no battery. It has no ticking heart. None of that back and forth stutter you hear inside a mechanical watch. And yet, it keeps time almost as well as the quartz chip in your phone. For about 300 years, every serious watchmaker on Earth agreed on one thing. A spring-powered watch could never be truly precise. The spring was the problem. It's analog, it's temperamental, it pushes hard when it's fully wound and weakly when it's running down. Precision came from electronics, and electronics needed a battery. One engineer refused to accept that trade-off. His name was Yoshikazu Akahane, and in 1977 he set out to build what he called an everlasting watch. The precision of quartz with no battery, no light, no radio signal, just a spring. It took him 28 years. His own company cancelled the project twice. His very first prototype ran for 4 hours before dying. And, this is the part that stays with you, Akahane passed away in 1998, roughly a year before the watch he'd chased for 2 decades finally reached the shops. He never saw it succeed. So this is really 2 mysteries in one. First, how do you make a lump of coiled steel keep time like a computer chip? And second, why did it take one of the greatest watchmaking companies in history nearly 30 years to do it? To answer that, we need to crack 3 questions. 1. If there's no battery, where does the electricity come from? 2. If there's no ticking escapement, what stops that spring from unwinding all at once in a couple of seconds? And 3. It borrows the exact same quartz crystal you'd find in a 5-pound wall clock. So, why isn't it as accurate as quartz? And how did Seiko's 2025 version very nearly close that gap? Stick around, because the answer to all 3 is the same single beautiful loop of engineering. And once you see it, you can't unsee it. The principle right. Let's build this from zero. Assume you know nothing about watches. That's fine. Every mechanical watch, from a cheap one to a masterpiece, does 2 separate jobs. Job 1. Push. Something has to physically move the hands around the dial. Job 2. Count. Something has to release that pushing energy in even measured little doses. So the hands move at exactly the right speed and not too fast. The push comes from the mainspring. You wind it up by turning the crown or automatically as your wrist moves. And as it slowly uncoils, it drives a train of gears that turns the hands. Simple enough. The clever, difficult bit is the counting. In a normal mechanical watch, that job belongs to a component called the escapement, working with a balance wheel. It grabs the gear train and releases it, grabs and releases, thousands of times an hour. That's the ticking. That's the sound of a watch counting. And here's the catch that haunted watchmakers for centuries. The escapement is mechanical, and anything mechanical drifts. It speeds up and slows down with temperature. It's affected by gravity depending on which way the watch is lying. It wears out. It's the hardest working, thirstiest, most delicate part of the whole machine. A truly excellent mechanical watch, one certified to the highest standard, is still allowed to be off by -4 to +6 seconds every single day. Now think about a quartz watch. It's brilliantly accurate because it counts using a quartz crystal that vibrates at a rock-steady frequency. But it pays for that in 2 ways. It needs a battery, and a little electric motor drags the hands forward in tiny jumps. That's the tick of the seconds hand, hopping once a second, so the trade-off looked permanent. Mechanical, soulful, self-powered, but imprecise. Quartz, precise, but battery-dependent and a bit lifeless. Akahane looked at those 2 families and asked a heretical question. What if you kept the mechanical push, the spring, but replaced only the counting? What if a spring-driven watch could count using quartz, without ever plugging in a battery? On paper, gorgeous. In practice, it created a problem so hard it would get the project shut down not once, but twice. Because to count with quartz, you need electricity. And Akahane had banned the one thing that reliably provides it. The core, the wheel that glides. This is where the real engineering lives. And the neat thing about spring drive is that it's a chain. Every solution creates the next problem. So let's walk it link by link. Start with that troublesome escapement. Akahane's first move was radical. Get rid of it entirely. In its place, at the very end of the gear train, he put a wheel. Seiko calls it the glide wheel. And instead of stopping and starting thousands of times an hour like an escapement, this wheel does something no watch part had done before. It just spins, continuously, smoothly, 8 full turns every second. Think of the difference like this. A normal escapement is a dog on a lead that lunges and gets yanked back, lunges and gets yanked. Jerk, jerk, jerk. The glide wheel is a dog walking at a perfectly steady pace, guided by an invisible lead that never actually snaps tight. And that single design choice is why a spring drive, seconds hand, doesn't tick and doesn't stutter. It glides in one continuous silent sweep right around the dial. Seiko even nicknamed the whole thing the quiet revolution. No ticking, because nothing inside is starting and stopping. Beautiful, but a wheel that just spins freely opens up a rather dangerous hole. The brake that never touches hears the hole. In a normal watch, the escapement doesn't just count. It also restrains the spring. It holds the mainspring back, letting it out in tiny sips. Rip the escapement out, and there's nothing stopping the spring. It would unwind in one violent rush and empty itself in seconds. Useless. So Akahane needed to slow that glide wheel down, but without friction, because friction is exactly the wear and tear problem he was trying to escape. His answer? A magnetic brake. The glide wheel carries a small magnet. As it spins past a fixed coil, the circuit can push an electrical load through that coil, which creates magnetic resistance, a drag that slows the wheel. No pads, no contact, nothing touching. It's the exact same principle as the regenerative brakes on an electric car or a train. You slow the thing down with a magnetic field instead of grinding parts together, and this brake is fast. According to watch technical sources, it's applied and released up to 256 times every second, constantly nudging the wheel to hold it at exactly 8 turns a second. So now we can slow the wheel with a frictionless magnetic touch. But a brake on its own is stupid. It doesn't know when to squeeze or how hard. It needs a boss, the quartz brain. And here's where the quartz sneaks in, but not the way you'd expect. Sitting in the movement is a tiny quartz crystal, vibrating at 32,768 times a second, 32,768 hertz. If that number sounds oddly specific, it's because it's one of the most common frequencies in all of electronics. It's very likely the exact same crystal ticking away inside the cheap wall clock in your kitchen right now. A little circuit divides that steady vibration down into a clean reference beat. Now the integrated circuit, the brain, does one job. It constantly compares the real speed of the glide wheel against that perfect quartz reference. Wheels spinning a touch too fast? The brain tells the magnetic brake to squeeze a little harder. Too slow? Ease off. That's a closed control loop. If you've ever used cruise control in a car, you already understand it. You don't press the accelerator yourself. You set a target, and a computer makes dozens of tiny corrections a second to hold that exact speed. Spring drive is cruise control for a watch spring. The quartz sets the target. The brain watches. The brake corrects, round and round, which leaves one enormous problem standing. That quartz crystal, that brain, that brake, all of it runs on electricity. And Akahane had forbidden a battery. So, where on earth does the power come from? This is the wall the project smashed into, twice. The spring pays for its own leash. This is the link that killed spring drive in 1983, and again in 1994. To feed that quartz and that brain with no battery, there's only one possible power source in the entire watch: the mainspring itself. But here's the brutal catch. A watch mainspring produces a fantastically tiny amount of energy. And back in the 1980s, no integrated circuit on the planet could run on so little power. The chip simply drank too much. The dream was impossible not because the idea was wrong, but because the electronics of the era weren't good enough yet. Akahane's first prototype in 1982 proved the concept worked, and then died after just 4 hours. The target was 48 hours, enough to run through a weekend. He was off by a factor that needed the chip to become around 100 times more efficient. So in 1983, the project was shelved to wait for technology to catch up. They restarted in 1993, and the prototype still guzzled roughly 5 times too much power. Cancelled again in 1994. The breakthrough, when it finally came in the late 90s, was a custom ultra-low power chip. And that unlocked the loveliest trick in the whole watch. Remember that glide wheel spinning past the coil? It doesn't just get braked there. As its magnet sweeps past the coil, it generates a tiny electric current. Exactly like the dynamo on a bicycle light, where the spinning wheel itself powers the lamp. Grand Seiko uses that very comparison. So look at what that one wheel is doing, all at once. The mainspring spins it, so it's the regulator. Spinning, it generates the current, so it's the generator. And that current feeds the brain, which fires the magnetic brake back onto the same wheel. The mainspring powers the wheel powers the brain brakes the wheel, and braking the wheel is what controls how fast the mainspring is allowed to unwind. It's a closed circle that feeds itself. The spring quite literally pays for its own leash. That's the answer to the whole riddle. There's no hidden electronics fighting the mechanics. The mechanics and the electronics are the same act. There's one last bonus the spring gives you, and it's the reason collectors love this thing. Why the spring stays. A normal quartz watch moves its hands with a weak little electric motor. That's fine for thin, light hands. But it can't shove big, heavy ones around. Because spring drive still uses the mainspring to physically drive the hands, the quartz only regulates, it never pushes. It keeps the muscular torque of a mechanical watch. That means long, heavy hands, even solid gold ones, sweeping all the way to the edge of the dial. It's the precision of quartz married to the strength of a mechanical movement. A spring drive chronograph can even run its stopwatch function while holding both its 72-hour reserve and its accuracy, something a mechanical chronograph struggles to do because its power sags as you use it. So it glides, it's silent, it needs no battery, and it's tough. Which raises the obvious question, just how accurate is it? And here's the twist. It borrows the same quartz crystal as a cheap watch. So why isn't it quite as accurate as quartz? And how did Seiko, in 2025, get astonishingly close? Connection, failure, and the man who never saw it. First, connection. Because this shouldn't feel like a distant curiosity. Nearly every piece of physics inside this watch is already in your life. That 32,768 Hz crystal is in your microwave, your car key, half the digital devices you own. The dynamo trick that generates the power is the same induction that charges your phone wirelessly. And the contactless magnetic brake is the same idea slowing down electric cars and trains. Spring drive isn't exotic science. It's everyday physics, assembled with obsessive precision. Around 200 parts in a 3-hand model, over 300 in a chronograph, hand-assembled, adjusted to tolerances of 1/100th of a millimeter. Now, the failure mode, and I'm going to be honest here because this channel doesn't do marketing gloss. Spring drive brilliantly kills the escapement, the part that wears out and drinks oil in a normal watch. It's far less bothered by gravity, by knocks, by position, but it has one lingering weakness, and it's the quartz crystal itself. A quartz crystal's frequency drifts slightly with temperature and with age. So a standard spring drive is accurate to about 1 second a day, roughly 15 seconds a month. That crushes a mechanical chronometer, which is 5 to 10 times less accurate. But here's the humbling twist. A top-end pure quartz movement, Seiko's own 9F, is good to about 10 seconds a year. So, the cheap-sounding technology still beats standard spring drive on raw accuracy because pure quartz doesn't have a physical wheel and spring to regulate. It just drives the hands electrically. Spring drive is always paying a small accuracy tax for the privilege of running on a spring. And this is exactly the gap Seiko attacked in 2025. In April 2025, Grand Seiko released the Spring Drive UFA, ultra-fine accuracy, caliber 9RB2. It's the first spring drive, rated not per day, not per month, but per year. Give or take 20 seconds a year. That makes it, by Grand Seiko's own measure, the most accurate mainspring-powered wristwatch ever made. How? By hunting that quartz drift. They age the crystal for 3 months so it settles. They seal the crystal and its sensor in a vacuum, away from humidity and static. The chip reads the temperature 540 times a day and corrects for it. And for the first time ever in a spring drive, they added a regulation switch so a watchmaker can trim the drift during a service. Akahane's 4-hour prototype had become a watch that loses less time in a year than most watches lose in a week, which brings us back to Yoshikazu Akahane. He had the idea in 1977. He worked on it reportedly after hours and largely alone, for years before the company would even back it. He watched it get cancelled in 1983 and cancelled again in 1994. He pushed it back to life a third time in 1997. And in 1998, his team showed the technology to the world at Basel. And then, in 1998, at just 52 years old, about a year before the first spring drive watches went on sale, Akahane died. He never got to see it reach a single customer. He never saw it become a whole family of movements. He never saw the day, in 2025, when his spring-driven idea would keep time to 20 seconds a year. So, back to the question on the cover. How does a lump of coiled steel keep time like a computer chip, with no battery? Now you know it isn't a trick, and there's nothing hidden. The spring turns the wheel. The wheel makes the electricity. The electricity feeds the brain. The brain breaks the wheel. And breaking the wheel is what tames the spring. One closed loop, where the mechanical and the electronic aren't fighting, they're the same motion, powering and correcting each other, 32,000 times a second. A watch that, on paper, shouldn't work at all, dreamed up by a man who spent 28 years and his whole career proving that it could. And if a spring can now hit 20 seconds a year, it raises a strange question. Pure quartz is more accurate and it's almost free. So why did quartz nearly destroy the entire Swiss watch industry in the 1970s? And why do people still pay a fortune to get away from it? That's a war story for another video. Here's my question for the comments. Is spring drive the cleverest movement ever made, or an over-engineered answer to a problem quartz already solved? I genuinely go back and forth on it, and I want to hear your side. If this rewired how you think about what's ticking on your wrist, the subscribe button costs you nothing and helps this channel more than you'd think. There's a card on screen now for our teardown of the mechanical escapement, the very part Akahane threw away, if you want to see what he was actually rebelling against. Thanks for watching. I'll see you in the next one.